Hi, my name is Yu Wei Yan, and now I'm going to do my lab test. So based on the circuit given, when t is less than 0, the switch is closed and there will be no current to flow to these branches as this switch has made the circuit to be shorted. Initially, the current that flows to the inductor is 0 and the voltage at the capacitor is 0. So there will be no energy stored in inductor and capacitor as there will be no current to flow through there to charge them. And when t is equal to 0, the switch is open and the current source will allow the current to flow to these branches to charge the capacitor and the inductor. So the component we need are DC current source, switch, capacitor, inductor, and resistor. So I will set up the circuit by using multisim. So now I'm going to change the capacitor to 25 nano, inductor to 25 millihenry, and resistor I will change to 625 ohm. The current source will be 24 milliampere. And I need an oscilloscope to obtain the current that flow to the inductor, and I will use a current clamp. As the green arrow here indicate the downward flow, so the current clamp will measure the current that flow to downward. The oscilloscope will read the voltage across the inductor, and the current clamp will get the current that flow through the inductor. As I said, the ratio of voltage to current is 1 V per milliampere. It means that 1 volt will have 1 milliampere to flow through the inductor. If I set this to 5 volt, it means that there will be 5 volt with 1 milliampere to step. In my experiment, 1 volt will have 1 milliampere to flow through the inductor at that time. So now I'm going to run my simulation. As you can see, my circuit here is ready for t is less than 0, and the current source here will allow the current to flow through here, and the current will flow through the ground and to the earth. So there will be no current to charge the inductor and capacitor, and which has satisfied the circuit needed from the question. No current will flow here at t equals to as t is less than 0 since the switch is closed. So I'm going to run my simulation now. Now t is equal or more than 0. Okay, so now you may see my oscilloscope show a graph here. And I will make my T1, which is very close to 0 volt. And what I can say that based on the oscilloscope shows, when T equals to 27.419 microseconds, there will be a voltage across the inductor with 21.111 volt. And I can say that as my current clamp has a ratio of 1 volt per milliampere, so the current that flows through the inductor at this time we had a current flow of 21.111 milliampere. So in order to make my SLAB can be finished in a faster way, I will copy my circuit to 2 times. So I can obtain my observation for these 3 values by changing here. This will be 500 ohm. This will be 400 ohm. So now all my circuits here are ready for t is less than 0. So now t is equal or more than 0. So this is the observation for t is for R is 625. The second oscilloscope will have the value for R is equal to 500 ohm, and the third oscilloscope will have the value for 400 ohm. I will record my data by setting them to have the same time interval. Okay, now you may observe the graph for these 3 values, and I will let the T1 close to 0 volt. All the T1 will have the same value. And I will record the data from 0 to 300. If I want to obtain the data for 20, so all the T2 will have the same value as well. So now I may see my oscilloscope. all the T1 are the same, T2 are the same as well. So I'm going to do the data recording by using Excel. So I'll start from 0 first. And the time now is 20.968 microsecond. So microsecond here. And this is the milliampere. As I mentioned before, one book will have 1 milliampere. So 2.984 will have 2.984 milliampere. 2.698 milliampere. I equals to 400, there will be 2.473 milliampere to flow through at that time. And I will do until 300. So this is the way that I do my data recording based on the oscilloscope for these three resistance value. So now I have finished my data recording and I'm going to plot the graph. Okay, so this is a graph that I obtained based on the oscilloscope. So now I'm going to do the calculation based on the theory. So this is the formula that we derive by using the theory for each resistance for the inductor current. I'm going to insert the equation, the formula first. So this R equals 625 and I will insert this formula into this column. When T is equal to 20 microseconds, the current that flows through the inductor by having the resistance 625 ohms is 4.983298 milliampere. Now, this will insert this formula. So for R equals to 500 at T equals to 20 microseconds, they will have 4.588989 milliampere to flow through the inductor. Now for R equals to 400. So for R equals to 400, when T equals to 20 microseconds, there will be 4.164931 milliampere to flow through the inductor. And now I'm going to plot the graph. So this is a graph that I obtained by using the formula, and this is the graph that I obtained by using the oscilloscope, which is simulation. And by comparing these two graphs, I can say that the results are verified since they are look similar and very close to. So we know that the current source, DC current here is given 24 milliampere. The maximum current will be 24 milliampere. However, based on my result, when R equals to 625 ohms, it causes an underdamping. And when R equals to 500 ohms, it causes a critical damping. When R equals to 400, it causes an overdamping. Okay, now we refer to the R equals to 625 ohms. It causes an overshooting here. Since it exceeds the maximum current value, which is 24 milliampere, that we set in our DC current, which is 24 milliampere. And you can refer to the table here. These are the values that exceed 24 milliampere by using the formula, and these are the values that obtained from the simulation. Although when I equals 625 ohms, it can reach to the final current value 24 milliampere faster than the 500 and the 400. However, it causes an overshooting. When I was 500 and 400, they do not exceed the maximum current value 24 milliampere. I can refer to the table here. So what I can conclude that when I equals to 500, it's causing critical damping, and I can say that this is the most suitable value to be used in our circuit since it does not cause an overshooting and it can reach to the final value, which is 24 milliampere faster than the 400 ohm. If you want to obtain the 24 milliampere in a slower way, you can set your resistance to 400 ohms and cause an overdamping in your circuit. I think that's all from me. Thank you.